Okay. Hi, everyone. Thank you very much for joining today's session. So, let's just briefly get our unit specification. So today we're on our third tutorial, and we're going to look into understand technical aspect of AI-based systems, including modification and ethical consideration. So, in our previous tutorial, we looked into AI, how this has how the different aspect works with machine learning and deep learning. So we looked into the difference, how they create training model and with the outcome, with the results. Also, during our previous tutorial, we looked into deep learning and we looked into the approaches. We evaluated the approaches and we looked into the techniques and the tools that are now used. So for today's session, we're now going to explore the technical options to enhance performance on AI-based system. Also, we're going to demonstrate and benchmark a technical modification to the existing deployment of AI-based system to enhance its performance. So after any further ado, let's dive into our presentation. So what are we looking into as our indicative content for today's session? We're going to look into statistical methods, computational intelligence, and traditional symbolic AI. Then we'll now look into data collection, data sources, and assessment of data reliability to modify AI-based systems. So looking into our first learning outcome, we're now going to explore the technical option to enhance performance on AI-based systems. So what could be these technical options? We're now going to look into algorithm optimization. So as we all know, AI is based on machine learning. So we need to optimize our algorithm. So we're going now to refine or challenge algorithms to reduce computational complexity and also improve the speed. So the techniques now are going to have model grooming, where we're going to be removing redundant neurons or layers in neural networks. Algorithms switching, where this is now going to use faster, more efficient algorithms, such as random foster and gradient boosting. So in today's session, we'll also circle back into our gradient descendant concepts. Also, we need to look into hyperparameter tuning. So with fine-tuned model settings, this is now going to enhance performance. So what are the techniques for these? We're now looking into grid search and random search. So these are systematical tuning of model hyperparameters. Biases optimization, where we're now going to have more advanced method focusing on maximizing our model performance with less and fewer iterations. Data engineering, where we're now going to improve the quality and relevance of input data. So what are going to be the techniques for us to improve? We're now going to look into data augmentation, featuring engineering, and dimensional reduction. So with data augmenting, we're now going to increase the volume on diversity of training data. Feature engineering, we're now going to manually create additional features from existing data to provide better context. And dimensional reduction, we're going to use methods like PCA and autocoders to remove irrelevant features. Model architecture. What are we going to do with model architecture? We're now going to optimize our model structure for obviously a better result. And by doing so, we're now going to have ensemble learning and transfer learning, where with the first one, we're now going to combine multiple models, such as bagging, boosting, stacking, which is going to improve our robustness. Then also we're going to have transfer learning, where we're going to utilize pre-trained model to reduce training time and improve accuracy. Hardware acceleration, where we're going to leverage specialized hardware to speed up computation. And what are the benefits, the techniques for this? We're now going to look into our GPUs and TPUs, where we're going to utilize hardware with parallel processing power, and also edge computing, where we're now going to run AI model closer to data source to reduce latency. Distributed training. This we're now going to scale training process across all of our multiple machines. And the technique that will be involved now are going to be data parallelism and model parallelism, where with the first, we're going to split data across several machines and aggregate the model update. And while with the second, we're now going to distribute parts of the model across different hardwares. Now we're going to circle back into our back propagation, which we looked into our previous tutorial, where we looked into our transfer model. So we looked into forward propagation, and today's session, we now focus more into back propagation. So we know this is now the process of adjusting weight by looking at the difference between our prediction and our actual training results. So some basic step of back propagation. Basically, we're now going to obviously calculate the error. So where we are trying to minimize the error that we have. So how far our model can optimize from the actual output. After calculating our error, we have to look into minimum error, where we're going to check whether the error is minimized or not. We're going to update the parameters. So we're going to look if the error is huge, then we now have to update the parameters, such as our weight and our biases. And once this is now complete, we can now check the error, repeat the process until the error becomes minimum as possible. So once our model is now ready to make predictions, this will be the error. The error will now become minimum, and we can now feed some input into our model in order for us to retrieve an output. Gradient descent, where we looked into our previous tutorial. So gradient measures how much of our output of a function changes if we change the input a little. So with gradient is now defined that as the slope of a function where the biases step on. We now have the slope and the faster model to learn. So here's the attributes, where B is the new value and A is our current value, and Y, which is in the middle, is now therefore our learning rate. And we also have values for our gradient term. So types of gradients. So we have batch gradient, stochastic gradient, and mini batch gradient, where the first one is the method to calculate the margin of error, but only update the model once the entire data set has been evaluated. Stochastic gradient descendant, instead of updating the model once the data set has been evaluated, it does so after every training. Example, so the frequent update allows us to see the detail improvement until coverages. Mini batch gradient descendant, so with this method, it is now used for most often in deep learning and training neural network, and it is the combination of batch gradient descendant and stochastic gradient descendant. So what we know is that our data set is now divided into smaller batches and about 50 to 256. So they evaluate each of the batches separately. So what is a chain rule? So chain rule is going to state, helps us to differentiate composite functions. So it states we now have a derivative of f, and here is the example of it. So now we're looking into backpropagation learning algorithm, which we've looked into our previous tutorial as well. So we now know that a training input pattern is presented to network input layer. Then we have the network, which then propagates the input pattern from layers to layers to the output layer. Then our output pattern is now going to generate by our output layer. So in this pattern is different from the desired output, and an error is calculated. So the error is now propagated backwards through the network from our output layer to our input layer. Backpropagation algorithm also use gradient descendant method to minimize the error function with respect to the modified network weights. So we now know that a learning rate of a step size ranging from 0 to 1 is usually specified, which is now going to determine the magnitude of our weight changes. So we now know that a value of a small learning rate slows down to the process, while a large value might cause network oscillation in our weight space. So again, looking into our backpropagation, we now need to know that we need the desired output of the training with examples. So when it comes to weight training in backpropagation algorithm, we now look into the various steps that we need to carry out. So step one, we have to look into initialization, where we now set all the weight and the threshold, which are the bias, level of network, the random number uniformly distributed inside a small range. Step two, activation, where we're going to activate the backpropagation neural network by applying inputs. So we now are going to update the weight in the backpropagation network, propagating backward the error associated with our output neurons. So here we have an example of how this is now calculated. With our weight training in backpropagation algorithm, we now have to calculate the error of our gradient for the neurons in our hidden layers as well. So once this is now calculated, we now know that our input will now have an input signal, and we are now propagated through our network from left to right. When it comes to updating weight at output layer, so we now know that the rule of updating weight at the output layer is similar to the perceptor learning rule. So the weight correlation in the multi-layer network is now computed in this way. Error gradient is now determined as the derivative of the activation function multiplied by the error at the neuron output. Here we can see an example of how weight correlation when it comes to the hidden layers, where we have the calculation of our weight, and we can now represent the error gradient at our neuron through our hidden layers. Here we have our pseudocode for our backpropagation, and here's the algorithm. So with feed forward, we're now going forward in the neural network. So we will now compute the values for each layer. So we're doing a different process compared to our backpropagation. So again, the desired output for Y and current output is going to be 0, where we now have our cost function or loss function in MSE, which is our mean squared error, where this is now let's represent and C. So our cost function will now be equal to C. Again, we have similar reason for biases. When we are ready with the amount by each, we have to change the weight. So then we are now going to modify our weight and biases. And here's the calculation for changing the weight. So we also have example for forward pass. And also with backward pass, where the main goal of backward phase is to learn the gradient of loss function with respect to the different weight and bias by using the chain rule of differential calculus. So the gradient are used to update the weight and biases. Here we have an example of how we're going to be applying gradient descent for back propagation. Also, we have an example for weight update in the next hidden layers, where we now continue with the back propagation path to update the values of our weight and our biases, and the gradient with respect to these weight and biases will now depend on weight 5 and weight 8, and we'll now be using the old value, not the updated one. So this was everything for today's session. So if there's no any question for me, I'm just going to end this